Hello and welcome to the Sleepy Astronomer. Tonight we're going to look at something you've probably seen without really seeing, a faint smudge of light in the autumn sky that turns out to be far stranger, far larger, and far closer than almost anyone realized until very recently. That smudge is the Andromeda Galaxy, and for thousands of years human beings have looked up at it and wondered what it was. A little cloud, perhaps. A patch of luminous mist, something small and distant and entirely separate from us. For most of human history, we were wrong about all of it. If you're settling in for the first time, welcome aboard our journey through the cosmos. And if you've travelled with me before to explore the quiet wonders of space, it's wonderful to have you back among the stars. Tonight's journey is a little different. A detective story that spans centuries, where each clue brought us closer to an answer that nobody expected, and where the final revelation turns out to be just a little bit unsettling. Wherever you are tonight, settling in for rest or simply curious about that faint blur you might have glimpsed on a dark autumn evening, I'm so glad you're here. If this journey through Andromeda's true size helps you unwind or fills you with that particular kind of cosmic wonder that comes from discovering you were wrong about something important, feel free to give the video a like. And if you'd like to help other space enthusiasts discover these peaceful astronomical journeys, a subscription really does help the channel reach fellow dreamers looking for calming content to drift off to. It means the universe to me, and it helps build this wonderful community of curious minds and starlight admirers. So, find your most comfortable position and let's begin. Because tonight, we're going to answer a question that haunted astronomers for generations. Just how big is Andromeda, really? How far away is it? How massive? And why did it take us so long to get the answer right? The story starts with that smudge. On a clear night, away from city lights, you can see it with your naked eye, a faint, fuzzy patch in the constellation Andromeda, about the width of the full moon, but far, far dimmer. Ancient observers noticed it. They catalogued it. They had absolutely no idea what they were looking at. Was it a cloud of glowing gas within our own cosmic neighbourhood? Was it a cluster of stars too distant to resolve individually? Was it something else entirely? Something that didn't fit into any category they understood? The question seems simple enough. Point a telescope at something, measure it, figure out how far away it is, calculate its size. But Andromeda refused to give up its secrets easily. Every generation of astronomers thought they had it figured out. Every generation was wrong, or at least not quite right. The numbers kept changing, the estimates kept growing, and with each revision the implications became more profound. Because here's the thing about measuring cosmic distances and sizes. The bigger something is, and the closer it is, the more it matters to us. A small, distant galaxy is just a curiosity, a pretty smudge to catalogue and move on from. But a massive galaxy, close enough to influence our own, that's a different story entirely. For decades, astronomers argued about Andromeda's mass. Was it bigger than our Milky Way or smaller? Was it a rival, or were we the dominant galaxy in our cosmic neighbourhood? The answer mattered, and not just for cosmic scorekeeping. It mattered because these two galaxies, ours and Andromeda, are bound together by gravity, falling toward each other through the darkness. Whoever is more massive sets the terms of that encounter. And then, just a few years ago, we finally got our answer. Not through a single observation or measurement, but through the patient accumulation of data from space telescopes and cosmic surveys, from careful studies of how stars move and how dark matter halos extend far beyond the light we can see. The answer turned out to be surprising, humbling, and, if you think about it long enough, just a little bit unnerving. Because when we finally measured Andromeda properly, When we traced its dark matter halo and calculated its true extent, we discovered something that generations of astronomers had missed. Something that changes how we think about our place in the universe and our relationship to that faint smudge of light. We discovered that Andromeda is far larger than we thought, so large, in fact, that we're already inside it. But I'm getting ahead of myself. That revelation comes later, after we've traced the long, winding path of how we finally learned to measure cosmic giants. Tonight, we'll walk that path together, from ancient confusion to modern revelation, from centuries of wrong answers to the unsettling truth we finally uncovered. We'll meet the astronomers who argued about whether Andromeda was even a separate galaxy. We'll watch as new technologies revealed new mysteries. We'll see how dark matter, that invisible scaffolding that makes up most of the universe, completely changed our understanding of where galaxies end and empty space begins. And by the end, when we return to that same faint smudge you can see on any clear autumn night, you'll see it differently. You'll know what it really is. You'll understand why it took us so long to measure it properly. And you'll carry with you the strange knowledge that proximity, in cosmic terms, isn't always what it seems. So settle in, get comfortable, and let's begin our gentle journey through one of astronomy's greatest detective stories, the tale of how we finally learned to measure the unmeasurable and discovered that some cosmic neighbours are closer than they appear. The smudge that swallowed the sky is waiting. The story of understanding Andromeda begins, as so many astronomical stories do, with someone noticing something that didn't fit. Something wrong in the sky. In this case, that someone was a Persian astronomer named Abd al-Rahman al-Sufi, and the year was 964 CE, during what we sometimes call the Islamic Golden Age, a time when scholars in Baghdad and Persia were carefully preserving astronomical knowledge, while much of Europe had forgotten how to read the stars. Al-Sufi was working on an updated version of Ptolemy's star catalogue, checking ancient observations against what he could see from Isfahan. And there, in the constellation we now call Andromeda, he noted something that shouldn't exist according to the prevailing cosmology. A small cloud, a little cloud, he called it, which was perhaps the most honest description anyone would give it for the next 1,000 years. He had no idea what it was, just a fuzzy patch where no star should be. Dim enough that you had to know where to look, but definitely there, definitely real, definitely wrong. For centuries, that wrongness persisted. Medieval European astronomers, when they finally started looking up again after the Renaissance, saw the same thing Al-Sufi had seen. They didn't understand it any better, but they noted its position because that's what you do when something doesn't fit. You record it, you measure it, even when you can't explain it. Then in 1612, Simon Marius turned one of the new telescopes toward that little cloud and became the first European to see it magnified. The magnification didn't clarify matters. Through his primitive telescope, the cloud resolved into still a cloud, a soft glow. He compared it to candlelight seen through horn, luminous but diffuse, refusing to resolve into anything comprehensible. No stars, no structure, just wrongness, made larger. The problem was that fuzzy things in the sky violated the rules. Aristotle had laid down those rules more than 2,000 years earlier. The heavens were perfect, unchanging, made of a substance that didn't exist on Earth. Everything up there was either a star or a planet. Clean categories, clear boundaries. Fuzzy, nebulous objects didn't fit. They were cosmological errors that refused to go away. But there they were anyway, Andromeda's cloud, the Orion Nebula. Fuzzy patches scattered across the sky, accumulating in catalogues, resisting explanation. In 1774, Charles Messier, hunting for comets, got so annoyed at these objects confusing his searches that he catalogued them specifically to avoid them. The Andromeda Nebula became M31 in his list, number 31 on a list of things that were definitely not what he was looking for. Nobody knew what these nebulae were. Clouds of glowing gas, perhaps, distant star clusters too faint to resolve. Some speculated they might be separate systems of stars, island universes, as the philosopher Immanuel Kant called them, completely separate from our cosmic neighbourhood. But these were just guesses. Nobody could measure their distances, which meant nobody could determine their true nature. They were mysteries that resisted solution, puzzles that accumulated without answers. By the early 1900s, better telescopes revealed that some of these nebulae had spiral structures, beautiful pinwheels of light suggesting organised systems. M31, our Andromeda Nebula, was one of these spirals, but that just made the question more urgent. What were they? This is where the stakes become clear, because by 1920 there were two camps of astronomers who fundamentally disagreed about the nature of reality itself. One camp, led by Harlow Shapley, believed these spiral nebulae were part of our galaxy, clouds of gas scattered among the stars of the Milky Way. Everything we could see was part of one system. Our galaxy was the universe, and these fuzzy patches were just local decorations within it. The other camp, led by Heber Curtis, argued these spirals were separate galaxies, entire systems of stars so distant that millions of suns blurred into fuzzy glows. If Curtis was right, the universe was incomprehensibly larger than anyone had imagined, and our entire Milky Way was just one galaxy among countless others. In April 1920, these positions collided in what became known as the Great Debate, a public discussion held at the Smithsonian Museum of Natural History. Shapley and Curtis presented their cases, each armed with observations, each convinced they were right, each arguing for a different version of cosmic reality. The stakes couldn't have been higher. This wasn't just about measuring distances or classifying objects. This was about whether the universe was knowable, manageable, comprehensible, or whether it was vastly, terrifyingly larger than the human mind could comfortably contain. Shapley's argument had a certain appeal. He'd spent years studying globular clusters and had figured out that the Milky Way was much larger than anyone had thought, not thousands of light years across, but hundreds of thousands. It was enormous. And if our galaxy was that enormous, surely these relatively small-looking spiral nebulae had to be part of it. They were nearby, in cosmic terms, because if they were separate galaxies, they'd have to be unimaginably distant and unimaginably large. The universe would have to be absurdly bigger than necessary. Curtis had different evidence. Novae, stars that suddenly flare up in brightness, appeared in the Andromeda Nebula. Lots of them. But these novae were incredibly faint compared to novae in our own galaxy. The only reasonable explanation was distance. Vast distance. If Andromeda was millions of light years away, its novae would naturally appear faint, even if they were intrinsically as bright as nearby novae. There was also the rotation problem. Some of these nebulae were clearly spinning. You could see it in photographs taken years apart. But if they were gas clouds within our galaxy, the rotation speeds implied they should tear themselves apart, unless they were far more massive than gas clouds could be, unless they were enormous collections of stars, rotating sedately over millions of years. The spectroscopy was ambiguous. Some said the light looked like starlight, others said it looked like glowing gas. Neither side could claim definitive victory. What made this debate so intense wasn't just the observations, it was what accepting Curtis's position would mean. If these spiral nebulae were separate galaxies, then the universe was so large, so populated, so beyond human scale that it became almost meaningless. Our entire Milky Way, hundreds of billions of stars, everything we'd ever observed, our cosmic home, would be reduced to just one galaxy among countless others. This was humbling on a scale humans had experienced before, each time more difficult to absorb. Copernicus had shown Earth wasn't the centre of the solar system. Later observations proved the Sun wasn't the centre of the galaxy. Now Curtis was suggesting our entire galaxy was just another object in a universe so vast that vast stopped being an adequate word. Shapley's position offered psychological comfort. Yes, the Milky Way was larger than we'd thought, but it was still everything. We could still draw a boundary around the universe and say, this is it, and we're in it, and those fuzzy patches are just details. The debate ended without resolution. Both sides made compelling arguments. The audience that night probably walked away thinking it was roughly a draw, maybe slightly favouring Shapley because his universe felt more manageable. But scientific debates aren't decided by rhetoric. They're decided by observations, by someone finding a way to measure what couldn't be measured before, by someone producing evidence so clear it can't be argued with, that someone was already at work. Edwin Hubble, up on Mount Wilson in California, pointing the world's largest telescope at the Andromeda Nebula night after night, taking photographs, searching for something that would settle the question definitively. He was about to prove that Harlow Shapley had made the universe far too small, that Heber Curtis had been right about something extraordinary, right in ways that would make Andromeda even stranger, more massive and more significant than Curtis himself imagined. The great debate was over. What was coming next was proof, evidence, measurements that would crack open the cosmos and reveal that the universe was far larger than almost anyone had been willing to believe. And once we knew how large it was, once we could measure it properly, we'd eventually discover something even more unsettling, that distance and separation in cosmic terms aren't quite what they seem, and that some neighbours are far closer than anyone expected. Edwin Hubble was not by most accounts a particularly humble man. He spoke with a fake British accent, despite being from Missouri. He wore riding breeches and smoked a pipe in what seemed like calculated affectation. His colleagues sometimes found him insufferable, but he was brilliant, methodical, and he had access to the most powerful telescope on Earth, the 100-inch Hooker telescope at Mount Wilson Observatory, high above Los Angeles in the California mountains. Night after night in 1923 and 1924, Hubble pointed that massive telescope at the Andromeda Nebula and took long exposure photographs. He was hunting for novae, stars that suddenly flare up in brightness, because novae might help estimate distances. But what he found instead was something far more definitive, something that would shatter the comfortable boundaries of the known universe. He found variable stars, Cepheid variables specifically, and that discovery changed everything, whether anyone was ready for it or not. To understand why Cepheids mattered so much, we need to talk about Henrietta Swan Leavitt, who never got proper recognition during her lifetime, but who provided the key that would unlock cosmic distances. Leavitt worked at Harvard College Observatory in the early 1900s, at a time when women weren't allowed to operate telescopes but were hired as computers, human calculators who did the tedious work of analysing photographic plates. It was considered menial labour beneath the male astronomers. But that careful, repetitive observation of thousands of stars revealed patterns the theorists had missed. Leavitt studied Cepheid variables, stars that brighten and dim in regular cycles, and she noticed something remarkable. There was a direct relationship between how long a Cepheid cycle lasted and how intrinsically bright the star was. Longer period, brighter star. It was a cosmic yardstick, a way to measure distances across space. Because if you knew how bright a star really was, you could calculate how far away it must be based on how bright it appeared. The same way a candle 10 feet away looks dimmer than one 5 feet away, even though they're producing identical light. Leavitt published her period luminosity relationship in 1912. It should have revolutionized astronomy immediately. Instead, she continued working for $30 a week, analyzing more plates, rarely getting credit. She died in 1921, 2 years before Hubble used her work to prove the universe was incomprehensibly larger than anyone had imagined. So there's Hubble on Mount Wilson in October 1923 examining his photographic plates of Andromeda, and he spots a star that varies in brightness. He marks it with an N for nova. But then he checks earlier photographs and realizes this star's brightness follows a pattern. It's not a nova, it's a Cepheid variable. He crosses out the N and writes VAR. You can see his excitement in that exclamation point, preserved on the plate. Over the next several months, he found more Cepheids in Andromeda, measured their periods, used Leavitt's relationship to calculate their intrinsic brightness, then did the math to figure out how far away they had to be to appear as faint as they did. The answer was staggering, about 900,000 light-years. We know now this estimate was too low. Hubble was working with imperfect calibration, and there were complications he didn't understand about different Cepheid types. Modern measurements put Andromeda at 2.537 million light-years, nearly 3 times his initial number. But even that first conservative estimate was enough to settle the great debate with brutal finality. Because Shapley had calculated the Milky Way at about 300,000 light-years across. If Andromeda was 900,000 light-years away, 3 times the diameter of our entire galaxy, then it absolutely, definitively couldn't be part of the Milky Way. It had to be something else, another galaxy entirely. Separate, distant, enormous. Hubble announced his findings in 1925 and the universe expanded. Not physically, it had always been that large, but in human comprehension. In the mental map we carried, we went from living in a galaxy to living in a galaxy, one among countless others scattered through space we couldn't even properly measure. The philosophical earthquake that followed was profound, though it happened quietly in a way that seems almost anticlimactic. There were no riots, no religious crises, no widespread panic. Humanity just adjusted. We'd been cosmically humbled before. This was the same pattern one step further out. Our entire galaxy wasn't the universe. It was just one island in an ocean that stretched farther than telescopes could see. Harlow Shapley accepted the evidence gracefully, though it proved him wrong. That's how science works. The universe is what it is, and observations eventually reveal truth whether we're comfortable with it or not. But here's what's worth sitting with for a moment. Hubble's discovery didn't just prove Andromeda was far away. It proved we could measure cosmic distances, that we could map the universe, that the incomprehensible could be comprehended, at least in terms of numbers and distances. Leavitt had handed us a ruler that worked across millions of light-years. Suddenly the cosmos was measurable, which meant it was knowable, which meant we had to confront what knowing revealed. Over the next few years, astronomers used Cepheid variables to measure other spiral nebulae. They were all galaxies, all unthinkably distant, all containing billions of stars. The universe that had seemed large when we thought the Milky Way was everything suddenly became so vast it bordered on meaningless. And Andromeda, that little cloud Al-Sufi noted 1,000 years earlier, that fuzzy patch that confused Messier, that spiral nebula that sparked debate, was revealed to be magnificent, massive, a galaxy comparable to our own containing hundreds of billions of stars, so far away that its light took more than 2 million years to reach us. Think about that. When light left Andromeda to begin its journey toward Earth, our ancestors were barely recognizable as Homo sapiens. Just small groups in Africa, learning to control fire, making stone tools. That light travelled through empty space for millions of years while our species evolved, developed language, built civilizations, invented science, and finally built telescopes, powerful enough to catch those ancient photons and figure out where they came from. We were catching light older than our species, reading messages written in photons that began their journey before humanity existed. The poetic irony wasn't lost on astronomers of the time. We'd spent centuries assuming we were special, Earth at the centre, the Sun unique, our galaxy everything. Each time we'd been proven wrong, and yet somehow each discovery that made us less special also made us more curious. Proving we lived in one galaxy among billions didn't diminish us. It made the universe more interesting, more vast, more worthy of exploration. But Hubble's discovery left critical questions unanswered. We knew how far away Andromeda was approximately, but how massive, how big? Did it contain more stars than our galaxy, or fewer? Was it the dominant structure in our cosmic neighbourhood, or were we? These weren't just academic questions, because Andromeda wasn't sitting there peacefully. It was moving toward us. Back in 1912, before Hubble proved Andromeda was a separate galaxy, Vesto Slipher had measured its spectrum and discovered something odd. The spectral lines were blue-shifted. Andromeda was approaching at about 300 kilometers per second. Most distant objects showed red shifts. They were receding as the universe expanded. But Andromeda was coming closer. This raised a question nobody could fully answer yet. What happens when Andromeda and the Milky Way eventually meet? Collision, merger, near miss? And crucially, who dominates that encounter? Who's the heavyweight and who's the challenger? To answer those questions, we needed more than distance. We needed mass, and that turned out to be far, far harder than measuring distance. In fact, astronomers would argue about Andromeda's mass for nearly a century, getting wildly different answers, revising estimates up and down, until just a few years ago when we finally got measurements we could trust. The 1920s gave us Andromeda's distance and proved the universe was almost unimaginably large. But the puzzle of mass, the weight that determines gravitational destiny, would haunt us for decades. Through technological revolutions and theoretical breakthroughs, through the discovery of dark matter and the development of space telescopes, through generations of astronomers who thought they had it figured out, only to discover they'd missed something fundamental. Weight is destiny in a gravitational universe, and knowing Andromeda's true mass would tell us not just what it is, but what's going to happen. To us, to our galaxy, to this corner of the universe over the next few billion years. Hubble had opened the door to cosmic measurement, but the thing we most needed to measure, the mass that determines everything, remained stubbornly hidden, refusing to reveal itself easily, guarding its secrets for almost another century. Once you know how far away something is, the next question should be straightforward. How much does it weigh? We'd figured out distances across millions of light years. Surely measuring mass would be easier. It wasn't. And the decades we spent getting it wrong reveal something uncomfortable about how science actually works, not as a steady march toward truth, but as a stumbling progression through confident mistakes. For most of the 20th century, astronomers thought they knew how to weigh galaxies. You measured their light output, figured out what types of stars produced that light, and added it up. More light meant more stars, which meant more mass. Simple arithmetic. Except it turned out that weighing galaxies by their glow was like weighing an iceberg by measuring the part above water. You'd get an answer. You'd be wrong by a factor of 10 or more, but you wouldn't know you were wrong because you couldn't see what you were missing. Nobody knew that yet, so astronomers looked at Andromeda, measured its luminosity, made assumptions about stellar populations, and calculated its mass. Different astronomers got different answers. That's normal in science. But the estimates generally clustered around a few 100 billion times the mass of our Sun. That seemed reasonable. It matched roughly what we thought the Milky Way weighed. We were cosmic equals, more or less. When we eventually collided, and by the 1950s everyone knew we would collide, it would be a meeting of peers. Neither galaxy would dominate. Except then people started looking at how things moved around Andromeda, and the numbers stopped making sense. Andromeda has two companion galaxies, M32 and M110, both much smaller than Andromeda but still substantial. By measuring how fast these satellites orbit, you can calculate how much mass must be present to hold them in place. It's Newton's law applied on cosmic scales. The faster something orbits, and the farther out, the more mass must be pulling on it. When astronomers did these calculations, they got answers that didn't match. M32 and M110 were orbiting too fast, too far out, for Andromeda to weigh just a few 100 billion solar masses. The number suggested Andromeda was heavier, significantly heavier. But by how much? That's where everything fell apart. Through the 1970s, 1980s, 1990s, different research teams using different methods kept getting wildly different estimates. Some said 400 billion solar masses. Others said 1 trillion. A few suggested 1.5 trillion. These weren't small disagreements. These were factors of 2 or 3 separating the estimates. Like 3 people weighing the same object and getting measurements that varied by hundreds of pounds. Part of the problem was stellar populations. Different types of stars have vastly different mass-to-light ratios. A massive blue star produces enormous light, but burns out quickly. A small red dwarf barely glows, but can last trillions of years. If Andromeda's stars were mostly dim red dwarfs, it would be far more massive than if they were brighter giants. We couldn't count individual stars. Andromeda was too distant. We had to guess based on overall colour and spectrum. Different guesses, different masses. But there was something deeper wrong, something fundamental that would take decades to understand. The problem wasn't just about stars. The problem was that most of a galaxy's mass isn't in stars at all. In the 1970s, Vera Rubin was studying rotation curves, measurements of how fast different parts of galaxies spin. Basic physics says objects farther from the centre should orbit more slowly, just like outer planets move more slowly than inner planets. The Sun contains most of the solar system's mass, so its gravity dominates, and distant objects feel weaker pull. But that's not what Rubin found. The outer regions of galaxies rotated just as fast as inner regions, sometimes faster. The rotation curve stayed flat all the way to the visible edge and beyond. This made no sense unless there was additional mass out there. Invisible mass that didn't produce light. Mass extending far beyond the visible stars. This invisible matter would have to make up most of the galaxy's total mass to explain the rotation curves. We started calling it dark matter because we didn't know what else to call it. Matter that had mass that produced gravity, but that didn't interact with light. Undetectable except through gravitational effects. The realization that galaxies were mostly dark matter changed everything. Suddenly, measuring luminosity told you almost nothing about true mass. The stars we'd been measuring all along, the part we could see, were just the tip of the iceberg. Most of the galaxy was hidden in a vast halo of dark matter extending far beyond the visible disk. For Andromeda, this meant all those earlier estimates based on starlight were wrong. Not a little wrong, fundamentally, embarrassingly wrong. The galaxy was far more massive than its light suggested, but how much more massive depended on how far the dark matter halo extended and how dense it was at different distances, and those were nearly impossible to measure. Astronomers tried everything: rotation curves of outer gas clouds, orbits of globular clusters, movements of satellite galaxies, computer simulations of dark matter distribution. Every method gave different answers. Every paper seemed to revise the mass estimate up or down. By the early 2000s, the uncertainty had become almost absurd. Here was our nearest large galactic neighbour, one of the most studied objects in the night sky, and we couldn't agree on its mass to within a factor of 2. The frustration wasn't just academic. This uncertainty meant we couldn't answer fundamental questions. Was Andromeda larger than the Milky Way? If we were heading for a collision, which we definitely were, who would dominate? Would we be absorbed into a larger Andromeda, or would we be the primary galaxy that survived? These questions mattered, not just for cosmic pride, though there was definitely an element of galactic patriotism involved, but for understanding what the collision would actually look like. The more massive galaxy controls the merger dynamics. It determines which structures survive, where stars end up, what the final merged galaxy becomes. And we simply didn't know, couldn't measure it, kept getting it wrong despite decades of effort. There's something humbling about spending generations trying to measure something and repeatedly failing. Science presents itself as confident, as steadily progressing toward truth. But the reality is messier. Sometimes you spend decades convinced you're close to the answer, only to realize you've been measuring the wrong thing the entire time. The ancient Greeks had a word for this kind of overconfidence: hubris, excessive pride, the arrogance of thinking you understand more than you do. They told stories about people who claimed they could measure the unmeasurable, weigh the invisible, challenge the gods. These stories always ended badly. Modern science doesn't talk about hubris much. Maybe we should. Because the story of trying to measure Andromeda's mass is fundamentally a story about overconfidence. Every generation thought they had it figured out. Every generation published confident papers with precise numbers. Every generation was proven wrong by better instruments and deeper understanding. The mass-to-light ratio problem should have been obvious in hindsight, but hindsight is easy. It's much harder to admit you're measuring the wrong thing when your methods give clear, measurable results. It's easier to trust numbers than to question whether the numbers mean what you think they mean. By the early 2000s, the scientific community knew they needed a completely different approach. Not just better measurements of visible stars or rotation curves, but ways to measure the entire gravitational influence across vast distances. Ways to trace the dark matter halo itself, to map its extent and density. Ways to account for the 85% of the galaxy's mass that was hiding in plain sight, invisible but dominant. They needed space telescopes with unprecedented precision, computer models sophisticated enough to simulate billions of particles, decades of accumulated data brought together and analyzed with modern statistical techniques. They needed to wait for technology to catch up with the problem. They needed patience, humility, and the willingness to admit that previous generations had been confidently wrong, and that maybe, just maybe, our current understanding was also incomplete. Because in a gravitational universe, mass is destiny. Get the mass wrong, and you get everything else wrong too. All your predictions about the collision, about the merger, about what happens over the next few billion years, all of that depends on knowing how much each galaxy weighs. For decades, we didn't know. We thought we knew, which was perhaps worse than admitting ignorance. We had numbers, measurements, published papers. We just didn't have the truth. The truth was coming, though. The instruments that would finally solve this century-old puzzle were being built, being launched, accumulating data night by night. We just had to wait a little longer, be a little more patient, accept that this particular cosmic secret had kept itself hidden for almost a century and wasn't going to give itself up easily. But first, we needed to understand what we were really trying to measure. Not just Andromeda's visible stars, but the vast invisible halo of dark matter surrounding it, the scaffolding that contained most of its mass, the architecture that would eventually reach across space and touch us. There's a story that the ancient Greek philosopher Plato told about prisoners chained in a cave, unable to turn their heads, watching shadows dance on the wall in front of them. The shadows were cast by objects passing in front of a fire behind them, but the prisoners couldn't see the objects or the fire, only the shadows. To them, the shadows were reality. They didn't know they were seeing only projections of something more fundamental, something real that they couldn't directly perceive. This is more or less our situation when it comes to galaxies. We see the stars, the luminous matter that produces light, and casts its glow across the cosmos. We photograph it, we measure it, we catalogue it. But the stars are just shadows in a sense. They're the visible manifestation of something much larger, much more massive that we cannot see directly. That something is dark matter, and understanding it is the key to understanding what galaxies really are, where they end, and how massive they truly are. Dark matter is one of the most frustrating concepts in modern astronomy, not because it's particularly complicated, but because it's so fundamentally strange. It's matter, it has mass, it exerts gravitational pull, it clumps together into structures. But it doesn't interact with light. It doesn't absorb light, doesn't emit light, doesn't reflect light. It's completely transparent to the entire electromagnetic spectrum. You could shine the brightest searchlight ever made directly through a cloud of dark matter, and the light would pass through completely undisturbed, as if the dark matter weren't even there. The only way we know dark matter exists at all is through its gravity. It pulls on things, it curves space around itself. It affects how galaxies rotate, how galaxy clusters hold together, how light bends as it passes through the universe. And when you add up all these gravitational effects, you realize that dark matter makes up about 85% of all the matter in the universe. Everything we can see, all the stars, all the planets, all the gas and dust clouds, every shining object we've ever observed, represents only about 15% of the universe's matter. We are living in a dark matter universe. The luminous matter is the exception, the unusual case, the tiny fraction that happens to interact with photons and therefore becomes visible to creatures like us who evolved to detect light. For a long time, this was just an abstract problem for cosmologists. Yes, galaxies had dark matter. Yes, it was mysterious. But the assumption was that the dark matter was mostly out there in the space between galaxies, filling the universe like an invisible cosmic background. The galaxies themselves, the visible collections of stars we could see and photograph, those were the real structures we should focus on. Then computer simulations changed everything. Starting in the 1970s and really accelerating through the 1980s and 1990s, astronomers started building sophisticated computer models of how galaxies form and evolve. They'd start with the conditions of the early universe, the tiny density fluctuations that existed shortly after the Big Bang, and let the simulation run forward, watching how gravity pulled matter together over billions of years. What these simulations revealed was startling. Dark matter didn't just fill the space between galaxies. It formed the fundamental scaffolding on which galaxies were built. Dark matter clumped together first, creating gravitational wells, deep pits in space-time where ordinary matter could fall and accumulate. The stars that we see formed later, gathering in the centers of these dark matter structures like sediment settling at the bottom of an invisible bowl. Every galaxy, according to these simulations, sits at the center of a vast dark matter halo, a roughly spherical cloud of invisible matter that extends far, far beyond the visible stars. The stars are just the bright core of a much larger structure, like a lantern in the middle of an enormous darkened room. The room defines the space. The lantern just makes one small part of it visible. For Andromeda, this meant that the galaxy we could see, that beautiful spiral of starlight spanning about 220,000 light-years across, was really just the luminous center of something much more massive. The dark matter halo extended perhaps 1,000,000 light-years or more, and it contained the vast majority of the galaxy's mass. The structure of these dark matter halos follows patterns that emerge naturally from the simulations. Near the center, dark matter is relatively dense. Not dense by everyday standards, but dense by the standards of cosmic space. As you move outward, the density drops, following what physicists call an NFW profile, named after the three researchers who first characterized it: Navarro, Frank, and White. The density falls off steadily, but never quite reaches zero. The halo just fades gradually into the background dark matter that fills all of space. This creates a philosophical problem. Where does the galaxy end? With visible matter, you can at least pretend there's a boundary. The stars fade out, the disk ends, you reach what looks like empty space. But with dark matter, there's no clear edge. The halo just becomes more and more diffuse, until eventually you can't tell where the galaxy's halo ends, and the general background of cosmic dark matter begins. It's like asking where Earth's atmosphere ends. There's no sharp boundary. The air just gets thinner and thinner until you're in space. But even in space, there are occasional atoms of hydrogen. The transition is gradual, fuzzy, impossible to pin down to a single altitude. The dark matter halos also aren't smooth and featureless. The simulations showed that they contain substructure, smaller clumps and streams of dark matter, remnants of smaller halos that fell into the main galaxy and got partially torn apart. These streams thread through the halo like invisible rivers, and occasionally a larger clump survives as a subhalo, a dense knot of dark matter that might host a small satellite galaxy. All of this invisible architecture was hidden from view until computer simulations revealed it, and even then, it was just theoretical. The simulations predicted these structures should exist, but we couldn't see them directly. We could only look for their effects, the way they influenced stellar motions, the way they bent light through gravitational lensing, the way satellite galaxies moved through them, like boats following invisible currents. Ancient cultures understood that there were layers of reality beyond what we could directly perceive. Hindu philosophy speaks of Maya, the veil of illusion that hides the true nature of reality behind apparent forms. Indigenous cultures around the world speak of spirit realms that coexist with the physical world, invisible but present, influencing events in ways we can only glimpse indirectly. Medieval cosmologists believed in celestial spheres, invisible structures that carried the planets across the sky, organising the heavens into perfect geometric forms, even though the spheres themselves couldn't be seen. They were wrong about the details, but they were right about the principle. There are invisible architectures that shape what we observe, structures that exist beyond the reach of our direct perception. Dark matter is our modern version of these hidden realms. It's the invisible scaffolding that holds galaxies together, the unseen foundation on which the visible universe is built. And like those ancient concepts of hidden reality, dark matter humbles us. It reminds us that what we can see is only a small fraction of what exists, that our eyes evolved to detect a narrow slice of the electromagnetic spectrum, give us only limited access to the true nature of the cosmos. For astronomers trying to measure Andromeda's mass, understanding dark matter halos was crucial, but also deeply frustrating, because measuring something invisible is inherently difficult. You can't just point a telescope at it. You have to infer its presence from how it affects things you can see. One method was to study the motions of stars and gas clouds far out in Andromeda's disk and beyond, measuring how fast they orbited and using that to calculate how much mass must be present to hold them in those orbits. But stars are sparse in the outer regions and gas clouds are faint, so getting precise measurements was challenging. Another method was to track Andromeda's satellite galaxies, small galaxies like M32 and M110 that orbit Andromeda like moons around a planet. By measuring their orbits, you could estimate the mass of the halo they were moving through, but this only told you about the halo's mass within the satellite's orbits. What about farther out? How much did the halo extend beyond the satellites? Gravitational lensing offered another approach. When light from a distant galaxy passes near a massive object like Andromeda, the object's gravity bends the light's path, creating distortions in the background galaxy's image. By measuring these distortions, you can map the distribution of mass, including dark matter, in the foreground object. But Andromeda isn't quite massive enough or positioned quite right to create strong lensing effects, so this method had limited usefulness. The computer simulations provided theoretical predictions about what Andromeda's halo should look like, how far it should extend, how its density should vary with distance from the center. But simulations are only as good as the assumptions you put into them, and there were still uncertainties about the exact properties of dark matter, how it clumps on different scales, how it responds to the formation of stars and galaxies within it. What astronomers really needed was a way to measure Andromeda's total gravitational influence across enormous distances, to map the entire dark matter halo from center to edge, to finally pin down where the galaxy ended and empty space began. But here's the thing they were beginning to suspect, based on those simulations and on measurements of other galaxies. The halos were bigger than anyone had expected. Much bigger. The visible parts of galaxies, the parts we'd been focusing on for centuries, were tiny compared to the dark matter structures they inhabited. For Andromeda, with its visible disk about 220,000 light-years across, the dark matter halo might extend 2 million light-years or more. That's roughly 10 times the diameter of the visible galaxy. Imagine if Earth's atmosphere extended 10 times farther than we thought, reaching out toward the moon. That's the kind of revision in scale we're talking about. And if Andromeda's dark matter halo extended 2 million light-years in all directions from its center, and if the Milky Way's dark matter halo extended roughly the same distance from our center, and if the two galaxies were only 2.5 million light-years apart center to center, well, you can see where this is going. The halos would touch. They might even overlap significantly. The invisible architectures surrounding both galaxies would intermingle in the space between them, creating a region where it wasn't clear which galaxy's gravitational influence dominated. where dark matter from both halos flowed together in complex patterns. This realization was building slowly through the 1990s and early 2000s, as simulations became more sophisticated and measurements of galactic halos improved. But it remained somewhat abstract, somewhat theoretical. The exact size of the halos was still uncertain. The degree of overlap, if any, was unclear. What astronomers needed was precise data. They needed measurements accurate enough to trace the dark matter halos to their edges. They needed to know, with confidence, how far these invisible structures extended. And in the 2010s, they finally got that data. New space telescopes with unprecedented precision, vast surveys mapping millions of stars, sophisticated analysis techniques that could extract weak signals from noisy data. The answer, when it came, was more unsettling than most people expected, but we're not quite there yet. First, we need to meet the instruments that solved the puzzle, the space telescopes that finally gave us the precision we needed to measure the invisible and discover just how close our nearest galactic neighbour really is. That's where we're heading next, into the era of space-based astronomy and the breakthrough measurements that finally, after a century of confusion and debate, told us exactly how massive Andromeda is, exactly how far its halo extends, and exactly what that means for us. Sometimes the solution to a problem isn't insight or cleverness. Sometimes it's just waiting for technology to catch up with the question you're asking. Waiting for instruments precise enough to measure what you need to measure. Waiting long enough that the truth can no longer hide. For Andromeda's mass, the waiting lasted nearly a century. From Hubble's 1925 discovery that it was a separate galaxy, to the breakthrough measurements in 2018 and 2019, astronomers kept trying to weigh this cosmic neighbour, kept getting uncertain answers, kept waiting for better tools. Those tools finally arrived. 2 space telescopes, each remarkable in its own way, each providing a piece of the puzzle that would reveal something nobody quite expected. The first was the Hubble Space Telescope, which by 2018 had been orbiting Earth for nearly 3 decades. Hubble had revolutionized astronomy in countless ways, but one of its less celebrated achievements was measuring tiny motions across the sky with extraordinary precision. Motions so subtle they'd be invisible from Earth's surface, blurred by atmospheric turbulence. But Hubble, above the atmosphere, could track them. The second was Gaia, launched by the European Space Agency in 2013. Its mission was ambitious: measure the positions, distances and motions of more than 1 billion stars in our galaxy. Create a 3-dimensional map showing not just where stars were, but how they move through space. The name Gaia comes from Greek mythology, the primordial goddess of Earth, the mother from whom all life emerged, the foundation beneath everything. It's fitting for a spacecraft dedicated to mapping our cosmic home. The ancient Greeks imagined Gaia as stable ground. Modern astronomers sent a spacecraft named Gaia to prove that nothing in the universe is stable. Everything moves, everything changes, and by measuring those motions precisely enough, you can uncover forces you can't directly see. What made these telescopes so powerful for solving Andromeda's mass puzzle was their combined approach. Hubble focused on Andromeda's halo, those faint old stars drifting far beyond the bright disk. Stars so dim you could barely see them, but Hubble could measure their positions precisely enough to detect how they moved over several years. Proper motion, astronomers call it, the sideways drift of objects as they orbit through space. These measurements are extraordinarily subtle. We're talking about angular movements smaller than the width of a human hair viewed from a kilometre away. But by measuring enough halo stars, you can map how they orbit, how fast they move, and therefore how much mass must be present to keep them in those orbits. The stars are test particles, revealing gravitational fields you can't see directly. Gaia, meanwhile, was measuring something complementary. It tracked stars in our own Milky Way with such precision that astronomers could detect Andromeda's subtle gravitational influence on our galaxy. Even at 2.5 million light-years away, Andromeda pulls on us. Not much, effects measured in fractions of kilometers per second, but with Gaia's precision, those effects became detectable. By combining Gaia's measurements of how we respond to Andromeda with Hubble's measurements of how Andromeda's own stars orbit, astronomers finally had enough information to calculate total mass with real confidence. The breakthrough papers appeared in 2018 and 2019. Different teams, slightly different methods, all converging on similar answers. Andromeda's total mass, stars, gas, dust, dark matter, was approximately 1 to 1.5 trillion times the mass of our Sun. And here's what surprised people. The Milky Way, measured with similar precision, had almost exactly the same mass. Not smaller, not significantly different. Roughly equal. We weren't the junior partner about to be absorbed by a larger neighbour. We were peers, equals. Two galaxies of comparable mass approaching each other through the darkness. This was a significant revision from earlier estimates that often suggested Andromeda was clearly more massive. The uncertainty had finally shrunk from factors of 2 or 3 down to maybe 20 or 30%. Not perfect, but good enough to answer the basic question, who's bigger? The answer was neither, or both. We were matched. But the measurements revealed something else, something that had been building slowly through all the previous observations and simulations, but that the precise data from Gaia and Hubble made unavoidable. By tracking stars and satellite galaxies at various distances from Andromeda's centre, by measuring orbital velocities in the outer halo, astronomers could finally map how far the dark matter halo extended. The results confirmed what simulations had suggested, but nobody had proven. The halo reached at least 1 million light-years from the galaxy's centre, possibly 2 million light-years or more. Some estimates put the halo's extent at roughly 2 million light-years from Andromeda's centre, a vast sphere of gravitational influence surrounding the visible galaxy, like an enormous invisible balloon. Now, Andromeda is 2.537 million light-years away from us. If its halo extends 2 million light-years in all directions, and if our halo extends roughly the same distance, then the math becomes unavoidable, uncomfortable, undeniable. The halos overlap. Not barely, not just touching at their edges. They overlap significantly by hundreds of thousands of light-years. There's an enormous region of space where both galaxies' dark matter halos intermingle, where the gravitational influence of both masses blends together, where asking which galaxy am I in stops having a clear answer. This was the revelation that nobody had stated explicitly until the precision data made it impossible to avoid. Andromeda and the Milky Way aren't just neighbours. They're dark matter halos. The invisible structures containing most of their mass interpenetrate in the space between them. We've been thinking of the collision as something that happens in the future, about 4 billion years from now, when the visible parts crash together. But in terms of dark matter halos, in terms of the majority of the mass, the interaction has already begun. This wasn't entirely surprising, given what astronomers understood about halo behaviour. Dark matter doesn't collide like ordinary matter. Two clouds of dark matter can pass right through each other, particles interacting only through gravity. So the overlap doesn't mean immediate chaos. It means a subtle, complex gravitational dance where matter from both halos flows and intermixes. but it did mean fundamentally reframing how we think about the relationship between our galaxy and Andromeda. We're not two separate objects approaching each other. We're already, in a real sense, part of the same system, already gravitationally entangled, already influencing each other's evolution in ways we're only beginning to understand. The satisfaction of finally solving the century-old puzzle was tempered by what the solution revealed. There's a moment in detective stories where solving the mystery makes things more complicated rather than less, where the answer raises more disturbing questions than it settles. That's where astronomy found itself in 2018 and 2019. We'd finally measured Andromeda properly, and the answer turned out to be, it's right here, already touching us, already surrounding us in its gravitational field, just as we surround it in ours. Hubble's legacy in this story carries a certain irony. Edwin Hubble proved in the 1920s that Andromeda was a separate galaxy, fundamentally expanding our conception of cosmic space and distance. Nearly a century later, the telescope named in his honour helped prove that separation isn't quite what it seems, that on the largest scales, accounting for invisible matter, the boundaries between galaxies blur into something far more ambiguous. Gaia, named for the Earth goddess who represented stability and foundation, revealed that our stable cosmic home is being pulled by forces from beyond, influenced by the gravity of an enormous neighbour whose domain already extends into ours. Between them, these instruments solved a problem that frustrated astronomers for generations. They did it through patience, precision, and years of accumulated observations. No single measurement was the breakthrough. It was the combination, the synthesis, the bringing together of multiple approaches until the picture finally became clear. And the picture that emerged was more unsettling than most expected. We now know Andromeda weighs roughly as much as we do. We know its dark matter halo extends at least 1 million light-years, probably 2 million or more. We know this halo isn't theoretical but measurable through stellar motions and gravitational effects. And we know, with a certainty no previous generation could claim, that this halo overlaps with ours, that the invisible architectures of both galaxies intermingle in the space between, creating a region where gravitational influences blend, where dark matter from both halos flows together, where the distinction between separate galaxies breaks down in everything but the visible light. The puzzle is solved. The mass mystery that lasted a century finally has an answer precise enough to build on. But solving that puzzle revealed a truth we weren't quite prepared for. We've been asking the wrong question all along. The question wasn't, how massive is Andromeda, or where does it end? The question was, how close is it really? And the answer, the one that took a century and space telescopes and billions of measurements to uncover, is closer than anyone imagined. Close enough that we're already inside its domain, and it's already inside ours. Close enough that the boundaries we assumed separated us dissolved the moment we measured them accurately enough to see their absence. There's something deeply human about our need to define boundaries, to say where one thing ends and another begins. We draw property lines, national borders, the edges of continents. We like to know what belongs to us and what doesn't, what's inside and what's outside, where home stops and foreign territory starts. But the universe doesn't particularly care about our need for clear boundaries. And nowhere is this more apparent than when you try to answer a seemingly simple question. Where does Andromeda actually end? If you look at photographs of Andromeda, those beautiful images captured by amateur astronomers with backyard telescopes or professionals with instruments that cost millions of dollars, you see a clear, defined object. A bright central bulge, spiral arms sweeping outward, the light gradually fading toward the edges until it disappears into the darkness of space. The galaxy appears to have an edge, a place where it stops and empty space begins. That visible disk, the part you can photograph with ordinary telescopes, spans about 220,000 light-years from one side to the other. It's larger than our own Milky Way's visible disk by a comfortable margin, roughly twice the diameter. If you were trying to define Andromeda's size based on what you could see, that would be your answer. About 220,000 light-years across. Done. Except that's not where the galaxy ends, not even close. Beyond the bright spiral disk lies the stellar halo, a vast, sparse collection of old stars that orbit the galaxy in a roughly spherical distribution. These stars aren't organized into spiral arms or a flat disk. They're scattered through three-dimensional space, forming a cloud that surrounds the visible galaxy like an enormous, nearly invisible sphere. The stellar halo is hard to see because these stars are so spread out. In the disk, you might have millions or billions of stars per cubic light-year in the densest regions. In the halo, you might have one star per cubic light-year, or even fewer. The stars are there, definitely there, but they're so thinly distributed that the halo doesn't glow with any appreciable brightness. You have to search for individual stars, catalogue them, measure their properties one by one to prove the halo exists at all. Astronomers have traced Andromeda's stellar halo out to about 1 million light-years from the galaxy's centre. At that distance, the stars are extraordinarily faint and sparse, but they're still there, still orbiting Andromeda, still gravitationally bound to the galaxy. They count as part of Andromeda in any meaningful sense. So is that where the galaxy ends? At 1 million light-years? Well, no, because beyond the stellar halo lies the dark matter halo, and that extends even farther. The dark matter halo, as we discussed earlier, is the invisible scaffolding that holds the whole galaxy together. It contains perhaps 85% of Andromeda's total mass, yet it produces no light whatsoever. We know it's there only through its gravitational effects, the way it influences the orbits of stars and satellite galaxies, the way it bends light passing through it, the way it shapes the large-scale structure of the galaxy. Computer simulations and observational data suggest that Andromeda's dark matter halo extends somewhere around 2 million light-years from the galaxy's centre, possibly farther. But here's the problem. The halo doesn't have a sharp edge. The density of dark matter just gradually decreases as you move outward. Near the centre, the dark matter is relatively concentrated. At 1 million light-years out, it's much more diffuse. At 2 million light-years, it's even more tenuous. And it never quite reaches zero. It just fades gradually into the background dark matter that fills all of space. This creates a fundamental problem for anyone trying to define where Andromeda ends. Do you draw the line where the visible stars stop? That seems arbitrary. You're defining the galaxy based only on the matter that happens to emit light, ignoring the majority of its mass. Do you draw the line where the stellar halo peters out? But that's also arbitrary. Why should old halo stars count more than dark matter in defining the galaxy's boundaries? Astronomers have come up with a technical definition to deal with this problem. They talk about the virial radius, a mathematical concept that represents the distance at which the galaxy's gravitational influence equals the expansion of space itself, the point where material orbiting the galaxy is barely held in place, and might, over vast timescales, drift away into intergalactic space. For Andromeda, the virial radius is somewhere around 2 million light-years, give or take. Within that radius, everything is gravitationally bound to the galaxy. It's part of Andromeda's gravitational sphere of influence, the region where Andromeda's mass dominates over all other forces. Beyond that radius, things get more ambiguous. But even the virial radius isn't a sharp boundary. It's a fuzzy transition zone where Andromeda's influence gradually weakens until it blends with the gravitational fields of other nearby galaxies and the large-scale structure of the universe itself. This fuzzy boundary problem isn't unique to Andromeda, of course. Every galaxy faces it. Our own Milky Way also has a visible disk, a stellar halo, and a dark matter halo that extends much farther than the stars. Our virial radius is roughly similar to Andromeda's, somewhere around 2 million light-years, possibly a bit less, possibly a bit more, depending on exactly how you calculate it. In a way, galaxies are less like islands, discrete, bounded objects, and more like organisms with permeable membranes. There's a dense core where most of the action happens, a region that gradually becomes less dense as you move outward, and eventually a point where it's hard to say whether you're still inside the organism or in the external environment. Ancient cosmologies understood this in their own way. The Ptolemaic system that dominated European thought for more than 1,000 years imagined the universe as a series of nested crystalline spheres, each carrying planets and stars, each sphere's influence extending beyond its visible surface. The boundary between one sphere and the next wasn't a hard edge, but a transition, a change in the organizing principle, a shift in which celestial mechanism held sway. Medieval philosophers argued about where Earth's influence ended and the moon's began, where the realm of change and decay gave way to the eternal perfection of the heavens. They never quite resolved it, because the universe resisted their attempts to impose clean boundaries on systems that were inherently transitional and interconnected. Indigenous cultures often had more flexible concepts of territory and boundaries. In many traditions, lands weren't owned but shared, with overlapping zones where multiple groups could hunt or gather, where the influence of different communities blended together. Sacred sites might belong to multiple peoples simultaneously, or to none of them exclusively. They were shared spaces where boundaries became meaningless. There's wisdom in that approach, particularly when dealing with cosmic structures that refuse to respect our desire for clear definitions. The way astronomers detect the extent of Andromeda's halo reveals just how fuzzy these boundaries really are. They look for stellar streams, long, thin ribbons of stars that were once small satellite galaxies, but have been torn apart by Andromeda's tidal forces. These streams can stretch for hundreds of thousands of light-years, marking the outer reaches of Andromeda's gravitational influence. But the streams themselves are disrupted structures. They're evidence of the galaxy's reach, but they are also proof that Andromeda isn't a coherent, defined object out at those distances. It's more like a gravitational influence that acts on whatever passes through it. Satellite galaxies provide another way to trace the halo. Andromeda has dozens of small companion galaxies orbiting it. M32 and M110 are the most prominent, but there are many others, most of them dwarf galaxies barely visible from Earth. Some of these satellites orbit more than 1 million light-years from Andromeda's center. They're definitely part of Andromeda's system, gravitationally bound to it. But they're so far out that they're also beginning to feel the gravitational influence of other nearby galaxies, including our own Milky Way. Perhaps the most clever method for detecting the halo's extent involves quasars, those brilliant beacons powered by supermassive black holes in distant galaxies billions of light-years away. When light from a quasar passes through Andromeda's halo on its way to Earth, the gas in the halo absorbs light at specific wavelengths, creating absorption lines in the quasar's spectrum. By studying many quasars whose light passes through different parts of Andromeda's halo, astronomers can map how far the gas extends. These studies show gas clouds more than 1 million light-years from Andromeda's center, thin and tenuous but definitely there, still part of the galaxy's extended atmosphere. The gas eventually fades into the intergalactic medium, the even more tenuous gas that fills the space between galaxies. But again, there's no sharp boundary, just a gradual transition from Andromeda's gas to intergalactic gas, with no clear point where one becomes the other. Our Milky Way has the same kind of fuzzy boundary. We have a stellar halo that extends hundreds of thousands of light-years from our centre. We have satellite galaxies, like the Magellanic Clouds, orbiting at the edge of our gravitational influence. We have a dark matter halo that stretches perhaps 2 million light-years or more, with the same kind of gradual fade into the cosmic background. And this is where the math becomes unavoidable. If Andromeda's halo extends roughly 2 million light-years from its centre, and if our halo extends roughly 2 million light-years from our centre, and if the distance between our centres is only 2.537 million light-years, then the halos don't just touch at their edges. They overlap significantly. Imagine two enormous fuzzy spheres, each about 4 million light-years in diameter, with their centres only 2.537 million light-years apart. The overlap region would be enormous, a volume of space hundreds of thousands of light-years across, where the gravitational influence of both galaxies blends together, where dark matter from both halos flows and mingles, where it's genuinely unclear which galaxy you're in. This isn't speculation or theoretical modelling. This is what the measurements from Gaia, Hubble and other instruments tell us. The halos overlap, right now, today, have been overlapping for millions of years, will continue overlapping for millions more. We've been thinking of Andromeda and the Milky Way as separate objects, two distinct galaxies that will collide in the distant future, but that's not quite accurate. In terms of the dark matter halos, in terms of the majority of the mass, we're already part of the same system, already interpenetrating, already, in a sense, beginning the merger. The visible parts of the galaxies, the stars, the gas, the spiral structures we photograph, are still separate. They won't come together for about 4 billion years, but those visible parts represent only 15% or so of the total mass. The other 85%, the dark matter that we can't see but that dominates the gravitational dynamics, is already interacting. This is the revelation that solving the mass puzzle led us to. Not just that Andromeda weighs roughly as much as we do, but that its influence extends so far, and our influence extends so far, that we're already inside each other's gravitational domains. The boundaries we thought separated us turn out to be fuzzy, permeable, already breached. There's something unsettling about this, isn't there? We're used to thinking of ourselves as residents of the Milky Way with Andromeda as a neighbour. Close, perhaps, but distinctly separate. Discovering that we're already inside Andromeda's halo, and Andromeda is already inside ours, changes that relationship. We're not just neighbours anymore. We're already entangled, already merged in the invisible architecture that contains most of our mass. The halo that doesn't end, it turns out, ends somewhere inside the halo of another galaxy, and that galaxy's halo ends somewhere inside ours. The boundaries we need don't exist. They never existed. We just didn't have the instruments to see their absence clearly until now. This is what happens when you finally measure something accurately enough. The answer you get isn't always the answer you expected. Sometimes the universe reveals itself to be more interconnected, more ambiguous, more complicated than the clean categories we try to impose on it. We wanted to know where Andromeda ended. We got an answer of sorts. It ends everywhere and nowhere, fading gradually into space, extending far enough that it already touches us, already holds us in its gravitational embrace, even as we hold it in ours. That's not the answer we were looking for, but it's the answer the universe gave us, and now we have to figure out what it means to live in a galaxy whose boundaries blend with the boundaries of its nearest large neighbour, to inhabit a space that belongs simultaneously to two enormous cosmic structures, to call home a region where the very concept of which galaxy am I in stops having a clear meaning. The overlap zone exists right now, around us, through us. The halo that doesn't end has already swallowed us, quietly, invisibly, across millions of years. We've been living inside Andromeda's domain all along without knowing it. We just finally noticed. Here's the thing that took us a century to figure out, the revelation that emerges when you finally measure everything precisely enough. We are already inside Andromeda's gravitational domain, right now, today, and have been for millions of years. The distance between the centre of the Milky Way and the centre of Andromeda is 2.537 million light-years. Andromeda's dark matter halo extends roughly 2 million light-years from its centre in all directions. Our dark matter halo extends roughly the same distance from our centre. The math is straightforward. The halos overlap by hundreds of thousands of light-years, creating an enormous region of space where both galaxies' gravitational influences blend together. We live somewhere in that overlap zone, not at the very centre of it, not at the edge, but somewhere within the vast volume of space where Andromeda's halo and the Milky Way's halo interpenetrate. This isn't speculation. This isn't a theoretical possibility. This is what the measurements tell us clearly and unambiguously. The dark matter halo of Andromeda reaches across the 2.5 million light-years that separate us and extends into the region of space we occupy. Meanwhile, our own dark matter halo reaches out toward Andromeda, extending into regions that are gravitationally dominated by that galaxy's enormous mass. There's something unsettling about this realization, isn't there? We've spent more than a century measuring Andromeda, calculating its distance, figuring out its mass, all while thinking of it as something separate, something over there, a neighbouring galaxy that we would eventually encounter in the distant future. The collision was a future event, scheduled for 4 billion years from now, safely remote in time. But that framing was wrong. The collision, or at least the beginning of it, isn't future, it's ongoing, has been ongoing for millions of years, will continue for millions more before the visible parts of the galaxies finally come together. The dark matter halos are already merging, slowly and quietly, in a process so gradual that it's invisible not just to our eyes but to our instruments, detectable only through careful statistical analysis of stellar motions and gravitational effects accumulated over vast distances and enormous timescales. Now, it's important to understand what overlap actually means in this context, because it's not like two solid objects colliding. Dark matter doesn't work that way. Dark matter particles, whatever they actually are, and we still don't know with certainty, don't interact with each other except through gravity. They don't collide, don't bounce off each other, don't create friction or heat or any of the phenomena we associate with ordinary matter crashing together. When two clouds of dark matter interpenetrate, they pass through each other like two clouds of mist merging on a foggy morning. The particles just keep orbiting according to the combined gravitational field created by both masses. Some particles that were originally part of Andromeda's halo find themselves pulled more strongly by the Milky Way's gravity. Some particles from our halo drift under Andromeda's influence. The gravitational fields blend and flow like water mixing with water. You can't point to a specific region and say, this is pure Andromeda, or this is pure Milky Way, anymore. It's both. It's a hybrid gravitational field created by two enormous masses whose spheres of influence overlap. This is why we don't feel it, why there's no observable effect in our immediate cosmic neighbourhood. The density of dark matter in galactic halos is extraordinarily low, maybe one dark matter particle per cubic metre at the distances where the halos overlap. That's incredibly tenuous by any standard. You could sit in a room for your entire life, and maybe a few dozen dark matter particles would pass through you. They'd interact with ordinary matter so weakly that you'd never notice. But gravity is cumulative. It doesn't care how diffuse the matter is, it cares about the total mass. And when you integrate all that tenuous dark matter across millions of cubic light years, when you add up the gravitational pull of trillions of solar masses worth of invisible particles, all tugging gently in the same general direction, the effects become significant over cosmic timescales. Satellite galaxies caught between the two giants feel this combined influence most acutely. The Magellanic Clouds, those two small irregular galaxies visible from Earth's southern hemisphere, orbit the Milky Way but are also being pulled by Andromeda's distant gravity. Some of Andromeda's own satellite galaxies, orbiting at the outer reaches of its halo, feel our gravitational influence competing with Andromeda's hold on them. Over millions of years, these combined gravitational effects can change orbits, strip gas from galaxies, trigger bursts of star formation, or send smaller galaxies careening off on new trajectories through the space between the two giants. The overlap zone is, in a sense, contested territory where neither galaxy has exclusive gravitational dominance. There's a Greek myth that feels relevant here, though perhaps not in the way you'd expect. Andromeda, the constellation's namesake, was a princess in Ethiopian mythology who was chained to a rock as a sacrifice to a sea monster. She couldn't escape, couldn't move, bound in place while a threat approached across the water. Perseus eventually saved her, in the traditional telling, but there's something about that image of being held in place, unable to move, watching something enormous approach that resonates with our situation. Except in our version, we're not being rescued. There's no Perseus. There's just the slow, patient, inevitable pull of gravity, binding us to Andromeda, just as Andromeda is bound to us. We're both the chained princess and the approaching threat, both held in place and closing in, both locked in an embrace that neither of us chose but that neither of us can escape. The irony of naming this galaxy after a princess who needed saving isn't lost on astronomers. Andromeda doesn't need saving. Neither do we. We're both massive, powerful structures, roughly equal in size and gravitational influence. What we're experiencing isn't rescue or destruction, it's merger. Two comparable entities becoming one, gradually, across billions of years, in a process that has already begun in the invisible scaffolding that contains most of our mass. Buddhist philosophy has a concept called interpenetration, the idea that all things contain all other things, that boundaries between objects are illusory, that separation is a convenient fiction we maintain to make sense of a reality that is fundamentally interconnected. The classic metaphor is Indra's net, a vast cosmic web where at each intersection sits a jewel that reflects all the other jewels, containing images of every other point in the net, infinitely mirrored and interconnected. Modern physics, in its own way, has arrived at something similar. The universe isn't made of separate, discrete objects cleanly divided from each other. It's made of fields and forces that blend together, of particles that exist in quantum superposition across multiple states, of gravitational wells that extend infinitely and therefore touch everything. The boundaries we perceive are convenient approximations, useful fictions that help us navigate reality but don't represent fundamental truths. Andromeda and the Milky Way, Seen from this perspective, we're never truly separate. We've been gravitationally bound since both galaxies formed, locked in a slow orbital dance that will eventually bring us together. The halos overlapping just makes explicit what was always implicit, that we were never isolated islands but always part of the same system, always influencing each other across the darkness. But there's still something invasive about it, isn't there? Something that feels like a violation of personal space on a cosmic scale. We thought we had our own galaxy, our own cosmic home, a place that was ours and not anyone else's. Discovering that Andromeda's gravitational influence already extends into our space, that we're already within its domain, feels like finding out that your neighbour's property line actually runs through your living room. It changes how you think about home, about sovereignty, about what it means to belong to a place when that place simultaneously belongs to something else. The merger, we've been told, happens in 4 billion years, but that's just when the visible parts come together, when the stars and gas and dust finally collide in spectacular fashion. The dark matter, halos, the majority of the mass, are already merging, have been for millions of years. The countdown isn't to when the merger begins. The countdown is to when it becomes visible, when the 15% of matter that happens to emit light finally catches up with the 85% that's been merging all along. We're living through the opening stages of a galactic collision, not watching it approach, living through it, right now. The gravitational tides are already shifting, slowly and subtly, in ways we're only beginning to detect. The satellites are already feeling the combined pull. The dark matter is already mixing, flowing, creating new gravitational patterns that will eventually reshape both galaxies into something neither would have become alone. There's a certain privilege in this knowledge, strange as that might sound. For millions of years, life on Earth, if any existed, would have been completely unaware that this was happening. Even after humans evolved, for thousands of years we looked up at that faint smudge in the sky, without understanding what it was. For most of human history, we didn't even know galaxies existed as separate objects, much less that we were locked in a slow gravitational merger with our nearest large neighbour. We're among the first generations to know this, to understand not just that Andromeda exists, not just that it's another galaxy, not just that we'll eventually collide, but that the collision has already begun in the invisible architecture that makes up most of both galaxies' mass. We're living through cosmic history, aware of it, able to measure it and model it and understand what it means. That awareness doesn't change the physics. Andromeda's halo would overlap with ours whether we knew about it or not. The merger would proceed on its billion-year timeline regardless of whether any conscious beings existed to observe it. But knowing changes something anyway. It changes how we think about our place in the cosmos, about isolation and connection, about boundaries and belonging. We're not isolated, we never were. The universe is more interconnected than it appears, more entangled, more intimate in its gravitational embrace. What seems separate is already touching. What seems distant is already here. What seems future is already present, unfolding slowly across timescales that human minds can barely comprehend. The faint smudge of light that Al-Sufi noted more than 1,000 years ago, that confused astronomers for centuries, that finally revealed itself to be another galaxy only a century ago, that smudge already owns us. Its gravity already holds us. Its dark matter, halo, already surrounds us. We've been inside it all along, living in the overlap zone, resident in a space that belongs to both galaxies, and fully to neither. This is what it means to finally measure something accurately enough. The answer you get isn't always comfortable. Sometimes the universe reveals itself to be closer, more intimate, more immediate than you wanted it to be. Sometimes the boundaries you thought protected you turn out to be permeable, already crossed, already meaningless. We are inside Andromeda's halo. Andromeda is inside ours. The distinction between the two galaxies, clear enough when you look at photographs of bright spiral arms, dissolves when you account for the invisible mass that dominates both structures. In the most fundamental sense, measured in terms of gravitational influence and dark matter distribution, we're already one system, just waiting for the visible parts to catch up with the reality that the dark matter has already embraced. So we're living in the overlap zone, in a region of space where Andromeda's gravitational influence mingles with our own galaxy's pull. What does that actually mean for us? For Earth, for the solar system, for the stars around us, for anything we might observe or measure on human timescales? The honest answer is almost nothing detectable. Not yet, not for a very long time. The gravitational influence from Andromeda at our location is real but vanishingly small. If you could somehow measure the gravitational acceleration that Andromeda's mass exerts on our solar system, you'd get a number around 1/billionth of a meter per second squared. That's 1 nanometer per second squared if you prefer. A nanometer is 1/billionth of a meter, roughly the width of a few atoms. This is not an acceleration you're going to feel. It's not going to change Earth's orbit around the Sun by any measurable amount in your lifetime, or in 1,000 lifetimes. The Sun's gravity dominates our local neighbourhood so completely that Andromeda's distant pull is lost in the rounding errors of celestial mechanics. But, and this is important, gravity is patient. It accumulates. That tiny acceleration, acting continuously over millions and billions of years, adds up. The trajectories of objects in the overlap zone are being subtly altered, bent toward Andromeda, just as they're bent toward the Milky Way's centre, following the combined gravitational field created by both enormous masses. The collision clock, in this sense, is already ticking, not counting down to when the merger begins, but counting through the merger process itself. We're in the early stages, the gentle approach phase, where the gravitational influences are present, but not yet dramatic. But every year that passes, both galaxies fall slightly closer together. Every million years, the gravitational binding between them strengthens. The process is underway. Think of it like climate change in a way, another example of invisible processes creating effects too slow for human perception, but undeniably real and accumulating. You can't feel the planet warming on any given day, but the temperature trend over decades is unmistakable. You can't see carbon dioxide molecules in the atmosphere, but their effects on global climate are measurable and significant. The cause and the effect are separated by timescales that make it easy to ignore, easy to think of as someone else's problem, easy to file away as future rather than present. But the present is when the process is happening. The future is just when we'll see the most dramatic consequences. The objects that feel this overlap most acutely aren't stars in galactic disks like our Sun. They're the satellite galaxies and globular clusters and high-velocity clouds caught between the two gravitational giants, orbiting at the outer reaches of both halos, where the competing influences create complex dynamics. The Magellanic Clouds, those two irregular galaxies visible from Earth's southern hemisphere, orbit the Milky Way at distances of about 160,000 and 200,000 light-years. They're well within our gravitational domain, but they're also close enough to the overlap zone that Andromeda's distant pull affects their long-term trajectories. Computer simulations suggest that the clouds' orbits are being perturbed by the combined gravitational field, possibly even enough to eventually strip gas from them or alter their paths through space. Andromeda's own satellite galaxies face similar complications. M32 and M110, those two small elliptical galaxies orbiting Andromeda, are held firmly in their parent galaxy's grip for now. But as the merger progresses, as the two dark matter halos continue to interpenetrate and blend, some of Andromeda's satellites will find themselves pulled equally by both galaxies. They'll end up in unstable orbits, eventually captured by one galaxy or the other, or possibly flung out into intergalactic space entirely. Then there are the high-velocity clouds, those mysterious concentrations of hydrogen gas moving through the halo at speeds that don't quite match the rotation of the galaxy. Some of these clouds might be gas falling into the Milky Way from the intergalactic medium. Others might be gas that was stripped from satellite galaxies by tidal forces. But some, and this is still being studied, might be gas being pulled between the two galaxies by the complex gravitational dynamics of the overlap zone. When gas clouds fall into a galaxy's disk, they create shock waves, compress existing gas, trigger bursts of star formation. If Andromeda's gravitational influence is already pulling gas around in the overlap zone, then some of the star formation we observe in our galaxy's outer regions might be indirectly influenced by our neighbour's presence. It's a subtle effect, hard to isolate from all the other processes affecting star formation, but it's potentially there, already shaping how our galaxy evolves. The dark matter itself, flowing through the overlap zone, behaves in ways that are difficult to visualize because we can't see it directly, but computer simulations give us a picture. Streams of dark matter particles, some originally part of Andromeda's halo, and some from ours, are mixing in the space between the galaxies. They don't collide, they just pass through each other, their trajectories bent by the combined gravitational field they collectively create. Over time, these flows create wake patterns, density variations, regions where dark matter from both galaxies has accumulated, and in regions where it's been pulled away. These variations, in turn, affect how gas flows through the overlap zone, which affects where stars can form, which affects the visible appearance and evolution of both galaxies. It's all connected, all influencing each other, all part of a single complex system, even though the visible parts of the galaxies are still more than 2 million light-years apart. But here's the crucial distinction. The dark matter halo merger is not the same thing as the stellar merger. The halos can overlap, interpenetrate, blend together, all while the visible galaxies remain separate. Because dark matter doesn't collide, it flows through itself. Stars and gas, by contrast, do collide, or at least they interact in dramatic ways when galaxies merge. The visible collision, the spectacular event that will reshape both galaxies into something new, is still about 4 billion years away. That's when the disks finally come together, when stars pass through each other's gravitational fields in close encounters, when gas clouds collide and ignite in enormous bursts of star formation, when the supermassive black holes at each galaxy's centre spiral together and merge. That future collision will be dramatic in ways the current halo overlap isn't. The night sky will transform over millions of years as Andromeda grows from a faint smudge to a massive, sprawling presence covering a substantial portion of the sky. Tidal tails, long streams of stars pulled out by gravitational forces, will stretch across the heavens. Star-forming regions will light up in brilliant pink and blue as gas clouds compress and ignite. The comfortable, familiar constellations will slowly distort and reform as stars from both galaxies intermingle. But even then, even during the visible collision 4 billion years from now, most individual stars will never directly collide with other stars. Space is mostly empty, even within galactic disks. Stars will have close gravitational encounters that change their orbits, but actual stellar collisions will be rare. Our Sun, if it still exists, and it will, though it will be well on its way to becoming a red giant, will probably pass through the merger without colliding with anything. What this all means is that the merger has stages, long stages. We're in the earliest stage now, the one where the invisible majority of both galaxies' mass is beginning to interact, while the visible minority remains separate. 4 billion years from now, we'll be in the middle stage, where the visible parts crash together in dramatic fashion, and then, another few billion years after that, we'll be in the final stage, where both galaxies have been completely transformed into a single, massive elliptical galaxy that astronomers have already nicknamed Milkomeda. From start to finish, the merger spans more than 6 billion years. We're perhaps 1 billion or 2 years into that process, depending on exactly when you start counting. The halos have been overlapping for millions of years already. They'll continue overlapping, with ever-increasing interpenetration, until the concept of separate halos becomes meaningless, and there's just one combined dark matter distribution surrounding one merged galaxy. There's something psychologically challenging about living through a process on this timescale. It's so slow that it might as well not be happening from a human perspective. Nothing in our lifetimes will change. Nothing in the lifetimes of our descendants for thousands of generations. The stars will look the same. The constellations will remain recognizable. Andromeda will stay a faint smudge in autumn skies, barely visible to the naked eye. But it is happening. The gravitational influences are real. The dark matter is mixing. The countdown is advancing, tick by imperceptible tick, toward an inevitable conclusion that will transform both galaxies beyond recognition. Ancient concepts of sovereignty and territory often included the idea of overlapping claims, shared domains where multiple authorities held partial sway. Medieval kingdoms had borderlands where the power of neighbouring realms blended together, where local lords might owe allegiance to multiple distant kings, where it wasn't always clear whose law applied. These were often unstable regions, contested spaces where conflicts erupted over questions of ultimate authority. The overlap zone between Andromeda and the Milky Way is something like that, except on a cosmic scale, and without any actual conflict. Neither galaxy is trying to dominate the other. There's no agency, no intention, no will. Just gravity, following mathematical laws with perfect indifference to questions of territory or sovereignty. But we still experience it in territorial terms, don't we? We think of the Milky Way as our galaxy, our cosmic home, our domain. Discovering that we're also inside Andromeda's domain feels like an encroachment, even though the physics couldn't care less about our feelings of cosmic ownership. Finding poetry in this situation requires a shift in perspective. Instead of seeing it as invasion or encroachment, perhaps we could see it as intimacy, as connection, as evidence that the universe is more tightly woven than it appears, that what seems separate is always, on some level, touching. Two galaxies, circling each other across millions of light years, already interpenetrating in their invisible structures, already merging in the matter that makes up most of their mass. It's a slow dance, a gradual embrace, a cosmic partnership that neither chose but both must participate in until they become something new together. There's terror in that, certainly, the loss of identity, the inevitability of transformation, the knowledge that this familiar cosmic home will someday cease to exist as a separate entity. But there's also something beautiful in it, something profound about being part of a process so vast and patient, about living in a universe where even galaxies are temporary, where structure and form are always in flux, where endings and beginnings blur together in transformations that span billions of years. We're living inside another galaxy's halo. That galaxy is living inside ours. The collision has already begun in the invisible architecture that makes up most of both structures. The countdown is already advanced, well past its starting point, ticking steadily forward through a process that will take longer than our species has existed and will continue long after we're gone. This is our cosmic address now, the overlap zone, the space between and within, the region where Andromeda and the Milky Way are both present, both influential, both part of the same gravitational system that will eventually merge them into a single entity. We thought we lived in a galaxy. Turns out we live in two galaxies simultaneously, in a space where the boundaries between them have already dissolved in everything but the light. The visible collision is still billions of years away, but the invisible one, the one that matters most in terms of mass and gravity and the fundamental forces shaping cosmic evolution, that one's already here. It's been here all along, we just finally figured out how to see it. So let's return to where we started, on a clear autumn night, looking up at that faint smudge of light in the constellation Andromeda, the same fuzzy patch that Al-Sufi noted more than 1,000 years ago. The same innocent little cloud that we spent centuries trying to understand. It looks exactly the same as it always has. Hasn't changed, hasn't grown brighter, hasn't moved appreciably across the sky. Just a dim blur requiring dark skies and patient eyes just to find it. But now you know what it really is, and knowing changes everything. We set out to answer a simple question. How big is Andromeda really? The answer turned out to be far more complicated and far more unsettling than anyone expected. It's massive, 1 to 1.5 trillion times the mass of our Sun. It's close, only 2.5 million light-years away, practically on our doorstep in cosmic terms. And it's enormous. Its dark matter halo extends roughly 2 million light-years from its center, creating a sphere of gravitational influence so vast that simple geometry tells you something you probably wish it didn't. We're already inside it. Not approaching it, not heading towards some future encounter. Inside it. Right now. The dark matter halo that contains most of Andromeda's mass reaches across the space between us and surrounds us in its gravitational field. Meanwhile, our own halo reaches toward Andromeda, creating an overlap zone hundreds of thousands of light-years across, where both galaxies' influences intermingle. This is the revelation that took a century to uncover. We thought we were measuring a distant neighbour. What we found instead was that distance and separation are more complicated than they appear. The boundaries we assumed existed between galaxies, clear, definite, protective, turned out to be fuzzy, permeable, already breached. The collision isn't coming. The collision has already begun, just slowly, quietly, in the invisible 85% of both galaxies' mass that we spent most of history not even knowing existed. 4 billion years from now, the visible parts will crash together in spectacular fashion, spiral arms distorting, stars scattering, the night sky transforming over millions of years into something unrecognizable. That's the collision we talk about, the one we can visualize, the one that sounds safely distant. But the dark matter has already been merging for millions of years. The gravitational influences are already present. The countdown isn't to when it begins. The countdown is to when the 15% of matter that happens to shine finally catches up with the reality the dark matter has been living all along. There's something deeply unsettling about this, isn't there? We like our boundaries. We like knowing where things are, what's ours and what's not, where home stops and foreign territory begins. discovering that a neighbouring galaxy's gravitational domain already extends into our space, that we're living in contested territory on a cosmic scale, that the separation we assumed was already compromised millions of years ago without anyone noticing. That knowledge sits uncomfortably. Ancient astronomers gave this galaxy a name, Andromeda, after the chained princess. They couldn't have known how apt that would turn out to be. We're bound to it, gravitationally locked in an embrace neither of us chose, falling toward each other with mathematical certainty, our fates entangled in ways that won't become fully visible for billions of years, but are already written in the trajectories of dark matter, particles flowing through the space between. So tonight, if you find yourself under dark skies, look for that smudge. It's still there, still faint, still innocent looking, but you'll see it differently now. You'll know that you're not just looking at it, you're inside it, living within its gravitational influence, held by forces that operate too slowly for human perception, but accumulate relentlessly across cosmic time. The measurement took a century. The revelation came as a surprise, and the truth that cosmic neighbours can be far closer than they appear, that boundaries dissolve when you measure them accurately enough, that we've been living inside another galaxy's domain all along, that truth changes how you think about isolation and connection and what it means to have a cosmic address. That faint smudge owns us, has owned us for millions of years, will continue to own us for billions more, until the distinction between our galaxy and their galaxy becomes meaningless, and there's just one merged structure containing all the stars from both. We finally know how big Andromeda really is. Big enough to reach across 2.5 million light-years. Big enough that we never stood outside it measuring from a distance. We were inside it the whole time, trying to measure something that already surrounded us. The collision isn't coming. It's here, just too slow to see, too patient to feel, too vast and gradual and inevitable to stop or avoid or even fully comprehend on human timescales. But it's here, in the dark matter flowing through the space around you, in the gravitational field that shapes trajectories you can't observe, in the slow, inexorable pull, bringing two massive galaxies together across billions of years. This is the Sleepy Astronomer, wishing you sweet dreams in the overlap zone, where the boundaries between galaxies have already dissolved, and what seems separate was never quite as distant as it looked.